Hi there, this video is for the first part of section 2.8. In this video, I'm going to briefly review slope and the instantaneous rate of change at a point, which is also known as the derivative of a function at a point. And then going to use the difference quotient to find the derivative at a point, and then explain how that generates the derivative function. And notice the key difference in vocabulary. Derivative at a point is a number. It's representing the slope of the tangent line, like the slope is 7, where the derivative function is a function. It's going to have an equation like, 3x squared plus e to the x or something. So we're going to introduce the derivative as a function. And that'll be good for this video. In the second half of the 2.8 video, I'm going to be talking about second derivatives and when the derivative doesn't exist. But we want to really get a handle of the derivative as a function, see what it looks like, see how it compares to the original graph of the function. That's our mission for this particular video. All right, so quick review of slope. This is just to have not a calculation, but just a good idea of what slope looks like. So this is kind of a mess with all these different lines, but I put a dot here at the origin so you can kind of see where the x-axis and the y-axis are, and they meet right here at the origin. So my goal here to help you review this idea of slopes is to just estimate each of these lines. This first diagonal line that I'm going to say right here, it is sort of at a 45-degree angle. I should mention that the x and y axes are assumed to be with the scale the same. So, one in the horizontal direction is the same as one in the vertical direction. So this red line, it goes through the origin and it has sort of a rise of one and a run of one. It's pretty much the same. So the slope would be approximately 1. So I'm going to ask you to pause the video and see if you can estimate the slopes of these other lines. And what I'm really looking for, is it a positive slope? Is it a negative slope? Is it larger than 1? Is it smaller than 1? That kind of thing. So please pause the video and see if you can estimate the slopes, not to super accuracy, but sort of the way I described. All right, so hopefully you did pause the video. Here are my approximations for the slopes of these lines. Again, you don't have to be precise, but you should have an idea of what's positive, what's negative, what's a bigger number, what's a smaller number. Verticals have an undefined slope. Horizontals have a 0 slope, that kind of thing. All right, so that was the idea behind this first exercise, was just to become familiar with approximating slopes. Believe it or not, this is a key to doing one of the harder types of problems in this section, is being good at just approximating slopes very quickly. Then you can start drawing graphs of derivatives and things like that also fairly quickly. All right, so our second little task here is to review the difference quotient. The difference quotient is what finds the instantaneous rate of change at a particular point, which is also known as the derivative at a point. So we've done a few of these before, so I'm going to do one just as a review. So this is the equation. It's some parabola thing. And we're going to look for the slope of that tangent line, which is the derivative at that particular point. The point I'm going to be using, as I've done before, is not specified. I'm not going to say at x equals 4. I'm just going to say at x equals a. So a is supposed to be some location that they'll specify later. So we're going to be using the difference quotient. There are two versions. I'll use this one. I think it's a little more common for Calc 1 students. There's the change in y, and then change in x actually gets simplified. X plus h minus x reduces down to h, and you got to remember your limit thingy thing there. Now we are at the point x equals a, so the first thing I can do is actually just plug in the value of a. I mean, if you knew the number, it might look a little bit better in some sense, but it is what it is. So that's what it is when I plug in the x value of a. Now I have to simplify this fraction by finding the function values. And the way we find function values is we literally use the function. So if we have an x value, the y value is given by our function, which was specified to be x squared plus 3x plus 1. So our first x value is a, and our second x value is a plus h. So those are the two things we need to plug in to, well, I guess we plug in a to the second one, but you get the idea. We're going to plug in these two into the function and therefore simplify our fraction. So when I plug in a, well, that means I just plug in the a into the x. So that gives me f of a, and nothing shocking here. It's just a squared plus 3a plus 1. I'm literally just plugging in a. Move me down here. For the second one, we need to do f of a plus h, and this is a little bit more algebra. We're going to have to plug in a plus h into the formula. So for this one, I'm going to get a plus h squared plus 3 times that a plus h plus 1. And I'll simplify this. I've done the simplification a few times already, so I'll do it a little bit faster this time. Hopefully, I don't make any errors. I have an a squared. Does anything actually combine together? It doesn't look like anything combines together, so I don't need to even write another line because it's just all that big old mess. All right, I don't have any variables or numbers that are the same. Okay, so we're going to continue our little limit here. F a plus h is given by this crazy thing, so I'm going to put that in thing for the f a plus h. So I get a squared plus 2ah plus h squared plus 3a plus 3h plus 1. That's just a f a plus h. I still need to do minus fa. Fa is this guy over here, so minus a squared plus 3a plus 1. And if you're good at algebra, you may remember, but it's this really entire thing that's being subtracted. So I highly recommend using parentheses so you don't make some sign errors. We still have this big division by h on the bottom. So that is currently our limit. All right, well, that is a lot of stuff. So let me see if things can simplify. I have an a squared, and I have minus a squared. A squared minus a squared is 0, so I don't have to write that. 2ah doesn't combine with anything, so I have to write my 2ah. Let me write my limit first. 2ah. I have an h squared, so that's enough. That cannot be combined. I do have this 3a and a minus 3a, so that's 0. Next, I have 3h, which does not simplify with anything else. And then I do have one more thing that simplifies, if you haven't seen it already. But here is a plus 1 and a minus plus 1. That's 0. So that is how the numerator of this fraction simplifies. The bottom is just h. Can't simplify that. But now I can divide or factor as you wish, right? So I can just factor an h out of the top. That's the way that the author of your textbook does it. And then h divided by h is 1. So this is 1 over 1. They divide equal 1, but multiplying or dividing by 1 does nothing. So I can just write this as the limit of 2a plus h plus 3. And the h value is getting infinitesimally close to 0 from both the right side and the left side. So I want values like 0.00000001 or negative 0.00001. But no matter what I choose, when I do, I didn't even notice I forgot my h. Oh, no, there it is. I divided it out. Yeah. So when I put in, sorry about that. When I put in h to be 0, almost exactly 0, positive or negative, this one's going to turn into 0. So I get 2a plus something infinitesimally close to 0, aka 0, plus 3. And so my answer for the slope of the tangent line at the point where x equals a is this expression right here. Whoops, I don't write the limit anymore because I just literally did the limit. So this is where you stop writing the limit. And I get 2a plus 3. So that's our answer to the original question, which was to find the slope of the tangent line at the point x equals a. All right, so that was a review of using the difference quotient. So we found this derivative at a point where we didn't specify the x value. We just said a, and a could be any number. So for example, suppose we had x equals 1. So in other words, we're using the number 1 instead of the letter a. So what would be the slope of the tangent line at the point where x equals 1? Well, that would be this formula, but I put in 1 instead of a, right? It's the exact same calculations, except there's going to be a 1 every time you see an a. So that should be 2 times 1 plus 3, or 5. So I know the slope of the tangent line to this graph at the point where x equals 1, the slope is 5. What about -2? Well, once again, I can plug in -2, and I can get the slope of the tangent line at the point where x equals -2. And I can do that for any point. At 0, if I plug in that x value, I can find, these are all slope values, right? This is a slope value. The slope value is equal to 5. The slope value is equal to -1. The slope value is equal to 0. Remember, our formula here, 2a plus 1, finds the slope of the tangent line at whatever point we specify, and I can make up whatever points I want. I just made up 3 as an example. All right, so why am I doing this? What's the point here? Well, a little bit of review, but more importantly, what I'm doing is showing you that we're basically creating a table of values. I have different x values, and for each different x value, I can find the slope value. So when I put in -2, I got a slope value of -1. When I put in 0, I got a slope value of, 0 plus 3 is not 0, by the way. Did you catch that? You know, when you think one way and write a different way, it doesn't help. 2 times 0 is 0 plus 3 is 3. So I'm glad I saw that error. 2 times -2 is -4 plus 3. So I didn't make a mistake on the previous one, but I did double check it. So when I plug in x0, I get 3 as an answer. And when I plugged in 1, I got 5. I haven't done -1 yet, but I could do -1 really fast. I just use my formula here. 2 times -1 is -2, plus 3 is 1. And so you have, for each x value, you have a slope value. Well, that's inputs and outputs. I input an x value, I output a slope value. That is the definition of a function. It has inputs and outputs, where each time you put an input, you get one output. Put in x equals -2, I get -1 as the output. The output is a slope. It doesn't really matter what the outputs are. You can interpret them how you wish. In this case, they are slopes, but that doesn't change the fact that this is, in fact, a function. And we can graph all these points. You know, I can say, okay, these are data points. I can say there's an x-axis. There's going to be sort of a y-axis, but I oftentimes write this as the slope, just to emphasize that we're not really graphing a y point. We're graphing a slope, because the y's are really up here, you know, in this equation. This is where you get the y values from the original equation. So, you know, even though your textbook writes y up there, I don't think that's as helpful as writing slope up here. I mean, we can use any letters we want, but sometimes it's helpful to remind ourselves that we're graphing slopes on the vertical axis. And I'm not going to try to make a good graph out of this. I'm just trying to emphasize a point that I can graph all of these points, -1, 1, 0, 3, 1, 5. It even maybe appear to be a linear relationship. This formula, this function, may even appear to be linear. Let's see if the rate of change is constant. From -1 to 1, I add 2, and that's a change of 1 in the x direction. So per 1x, I've gone up 2, and I've gone up 2, and I've gone up 2. So I'm going up 2 every single time the x goes up 1. So you can calculate slopes of these slopes. That makes sense. But you can see that it does go up by the same amount each time, +1 for the x's and +2 for the y's. So it really does form a straight line. Not that important, but it is maybe an interesting thing to think about, that in this particular case, our function, which is inputs x's, output slopes, is actually a line. So we call this thing the function of the slopes, the function of all of these possible inputs and outputs, where the input is x and the output is the tangent line slope. We call this the derivative of the function. So derivative at a point is a number. Derivative of a function is a function itself. In this case, the derivative of our original x squared type function looks like it's a linear function. And in fact, it is, right? So this is what we're going to be kind of building on a little bit more today. The fact that the derivative in general is a function, and it's found by using the derivative or difference quotient at any particular point A. And the formula for this derivative function is exactly this formula right here. And that may make sense if you kind of think about it. Every single time I put an x value, how do I find the slope value? Well, I plug it into the formula, right? That's what I did over and over again. That's the formula that I used to find the slope at each x value. So why are we using the letter A? I mean, why don't we just plug in x? So that's what the math people said. Okay, well, let's write this thing, instead of using this letter A, let's just write it using an x. So we say the derivative function, right, is the generic formula for derivative at a point x equals A, but we're using the letter x instead of A. So in this case, we write the derivative dy dx is 2x plus 3. That's this 2a plus 3 written in terms of x, or you can write it in terms of f prime x after the little hash mark there. If you have seen my previous video, I highly recommend that you learn it this way. This way is not as good. I mean, it's correct. You wouldn't lose any points, but there are more complicated formulas in Calc 1 and Calc 2 where you literally cannot use this version of the derivative. You have to use the dy dx version. And so if you learn the f prime x version, it may be hard to switch when you have to, right? So if you just learn the dy dx version, you never have to switch. You're always good for no matter what calculus or math you take. So my recommendation is this one on the left. If you're color sighted, it's the one I boxed in blue. It says dy dx is equal to 2x plus 3. Okay, so that was the idea of the derivative as a function. So anytime we have a function, whether it's x squared plus 3x plus 1 or any function, we can find the derivative function, which is the function that gives us any possible slope of a tangent line at any particular value of x that we plug into the formula. So there's a formula, you plug in a value of x, you get the slope at the point of the tangent line at that point. All right, so the thing they're going to have you do in this section is sort of play around with the idea that the function and the derivative function are related. And they want you to first see it visually. So I'm going to give you some examples. I'm just trying to put a break between here. So ignore this funny thing. So this is going to be the function. This is y equals fx. I'll put it over here. Y equals fx. So in other words, this is the x-axis, and this is the y-axis, and that's a function. And what we're going to do is below it is we're going to graph the derivative. So this is going to be the derivative function, f prime x, or more usefully, dy dx. Your author is the author of your textbook is, a very, well-studied mathematician who can instantly in their mind switch between f prime x and dy dx. If you feel that you can go right ahead. Again, I'm not going to take off any points, but I'm going to be writing dy dx to remind you of that that notation. So I'm going to write x here, and I'm going to write m up here because we're doing slopes. Again, the author of your book writes y up there. I have had many students who get confused. They even write it on the same axes sometimes, where the m-axis is superimposed on top of the y-axis. And then it becomes even more confusing when you're reading a vertical number. Is that vertical number a y number? Is it a slope number? Like, I just put them vertically on top and bottom so I can distinguish the two of them. So we are now going to graph the derivative function without even knowing the derivative formula. If I was given the function formula in this example D, I could do my difference quotient and I could find a formula for the derivative function I graph, but we're just going to graph the derivative function without knowing anything else except the graph of the original function. So just to remind you, the derivative function measures slopes. So we can actually estimate the slopes at a bunch of points. So what we're going to do is we're going to choose a bunch of points. Here's x equals 0. It doesn't really matter how you number them. You can number them 0, 1, 2, 3, 0, 5, 10. Doesn't really matter. I'm just going to make up some numbers. It doesn't really matter. The key thing is whatever numbers you put here, you're going to have to put the exact same numbers here. All right, so 0, 0, 1 is, I don't know if I put a 1 there. 1 is 1, 2 is 2. So they have to be lined up, right? Because we're going to be graphing right below it the slope. And we could do a -1 over here, -2. I don't know how many you want to do. You have to do enough until you can kind of see the pattern of what's going on, kind of when you first learn how to do graphing. All right, so for each of these points, we're going to approximate the slope. So how do we approximate the slope? Well, the slope is specifically the slope of the tangent line, and that means you have two infinitesimally close points, and we're going to draw the sort of line between those. One of the points has to be on the function itself, and the other one is supposed to be on the function, but infinitesimally close. So if I'm at 0, I could use the point like right at 0 and something infinitesimally close. I can't really draw infinitesimally close, so I'll do it sort of like close-ish, maybe a little bit closer, but it has to be on the function, right? So it has to be up here. It can't just be on the x-axis, right? Although in this particular case, it looks like it's pretty close to the x-axis right here. So then I draw the line, the tangent line. I mean, officially it's a secant line, but I draw that line through the point. And if those 2 points are really, really close to each other, what's the slope of that line? Well, it's a horizontal line. And if you remember our little exercise at the beginning of this video, horizontal lines have a slope of 0. So at this point, at the point where x equals 0, we have a slope of 0. So at this point 0, we know the slope is 0. Well, the vertical axis is the slope, so I'm going to put a dot here where the slope is 0. The slope of 1 might be up here, slope of 2 might be up here, slope of -1 might, so these are all slope values. When x equals 0, the slope is 0, so I'm going to put a 0 there. Let's do the same thing when x is 1. This is the dot on the graph where x equals 1. Take a point infinitesimally close, or as close as you're comfortable, draw a line. What's the slope of that line? Well, it's positive. It's a little bit less than 45 degrees, so it's going to be something smaller than 1. It doesn't really matter what you put, a half or whatever. It just, you were trying to approximate it. So I'll just say it's a slope of a half. So at this point, at x equals 1, we have a slope of 1/2 right there. So then we continue on. We're going to I'm going to erase this little line right here. We're going to look at the point when x equals 2. And remember, we're taking a point on the function. So when x equals 2, this is approximately where the function is. And you want to take a nearby point, and you want to approximate the slope through that point, the secant slope, which should be really, really close to the tangent slope. All right, so this is a good time for you to see if you could finish the dots, finish the slope approximations for all these numbers, -2, -1, 2, and 3, and then come back and I'll show you what I got in terms of the results of the slope or the derivative function. Okay, so hopefully you had a chance to do that. It turns out no matter where I look on this function, the slope is always positive. The last one I did was at -2. An adjacent point on the function still creates a positive rising line, a slope, and I approximated about 2 or something like that. And so the dots I got, they're down below here. Let me put them in a green or something. Here, just approximating it. That's what the graph of the derivative function looks like. More specifically, that's sort of the skeleton to connect the dots version of the function. If we connect these or use more additional points, remember, we can plug in more points. We can plug in -3 and find out the approximate, whoops, I got to plug in -3 and put it into the function, which would be down here. I can approximate all kinds of slopes until I'm confident I know what the derivative graph looks like. It will look something like this. And in fact, it is kind of a parabola shape for that particular function shape. The function shape originally is kind of like an x to the third type graph, and the derivative function is sort of like a parabola x squared type graph. So that's the idea of when you're given the graph of a function, we can therefore approximate the graph of the derivative function. All right, let's try this another time. Put me up here, I guess. So the second problem I have here, again, this is the function y, x. These are points. We're going to be graphing the slope, the derivative. So x horizontal and m is the vertical. We're going to be choosing a bunch of points. So you can choose them as you wish, and you can label them ABC or X0, X1, X2, or you can label them 0, 1, 2. You can label them any way you want, right? The only reason I label them is so that I have a reference frame of like where to put what. I mean, it's just a way of labeling things so I can, accurately approximate what it looks like on the graph below. So if I do some numbers like that, I'm going to do the same numbers with the same spacing down below. So I'll do those. And why did I choose these numbers? I mean, I don't know. You choose as many numbers as you need to be able to see the pattern. So that's supposed to be a 3 right there. Okay, so I am now going to invite you to pause the video and see if you can come up with the graph of the derivative of this function that I showed here on the top. So the goal here is to draw your tangent line slopes, approximate them, sort of mark the x slope value on the bottom graph until you have enough points to see a pattern, and that would be the graph of your derivative function. Okay, so of course your dots may look a little bit different depending on how you approximated those slopes, but it should look somewhat similar. I did add in one additional point, 6. After you do a few of these, you'll start realizing where a graph has like a peak or a valley, a vertex point like here, you're going to have a flat tangent line slope, which is going to be a 0. So right here, where I've labeled approximately x equals 2, the graph is right at the peak, which is going to have a slope, a tangent line slope of 0. And putting a 0 slope means you're putting the vertical axis at 0. So that's going to be really easy for us to sort of help see a pattern if we can spot those 0 slopes. So there's a 0 slope here at -2, and then I also drew in the one at 6. And I drew in some of the approximating slopes in between, and I get this sort of snaky graph. If I connect these dots, you get something looking like this. So and it continues. It doesn't stop there. I just didn't do some more dots. It continues this way as well. So the original function is this sort of wavy thing. It is sort of like a sine function, some version of a sine, if you remember what those things look like. And the derivative graph down below is another wavy function. It looks sort of like a cosine graph, if you remember what cosine graphs look like. So this is our exercise you'll be doing in section 2.8, where they'll give you a function and you'll want to graph the derivative by understanding the idea of slopes at points. I have last couple of examples. So we have a graph of a derivative, a graph of a function. What does the graph of the derivative look like? So again, this is just a visual separation. So here's my y-axis and my x-axis. This is essentially my slope axis, and the x-axis is down below. And now becomes your opportunity to try these two problems. This is the xy, and this is the slope x. Yeah, so pause here, see if you could figure those out. we're just looking for a sketch. So see if you can make a good sketch, and then unpause the video and I'll show you what I got as my answers. Okay, so hopefully you had a chance to try that. These are my skeletons for examples F and G. For F, we got a bunch of tangent line slopes that are getting flatter and flatter and flatter. They never really get negative or even zero, but they do get close to that. So that's represented right down here. And this part on the left-hand side, the tangent lines are very steep. So that represents a large positive slope. So on the left-hand side, you get things like this, has a very large positive slope at that x value. So once again, the bottom graph, we're sketching out the slope values at every point on the original function above. So if I connect those dots, I get something looking like this. So that's the graph of the derivative function if the graph of the original function is given above. And the last example here, G, we have a parabola. It has one sort of vertex right down here. So that's going to be where we have a zero slope. That's why there's a point right here. And then the slope goes up pretty consistently. It goes, slope of 1, slope of 2, slope of 3, things like that. And we end up getting something that's similar to a straight line. And this is like the original example I gave where we started with an x squared plus 3x plus 1 graph, which was an x squared type graph. And the derivative of the x squared type graph was a line graph. It was like 2x plus 3 or something like that. Here's another example of a parabola graph where the derivative function is a line, or at least appears to be a line. In fact, the derivative of any x squared type function is, in fact, going to be a linear function, as we will see in the beginning of chapter 3. All right, well, that's it for this video. We'll have another portion of 2.8, which is much shorter than this, which is talking about the second derivative and when derivatives do not exist. And then we are finished with chapter 2. All right, well, hopefully you found this video helpful. And please reach out if you have any questions or need additional examples or anything of the sort. All right, have a good day.